Welcome to a peaceful journey through the hunt for alien life. Every method, every discovery, every possibility. Tonight, I invite you to join me on a gentle voyage through some of the most fascinating aspects of our universe. As you settle in and close your eyes, imagine yourself floating weightlessly in the vast expanse of space, surrounded by the gentle glow of distant stars. We're going to explore 6 interconnected aspects of the hunt for alien life. Every method, every discovery, every possibility, each flowing naturally into the next, like celestial bodies in their eternal, peaceful dance. Let yourself relax as we drift together through these cosmic wonders. We begin our gentle journey by simply pausing to consider the grand, silent canvas of the cosmos. Imagine drifting quietly through the vastness, observing the slow, patient unfolding of creation. Before any complex life could emerge, before even the formation of planets, the fundamental ingredients had to be meticulously prepared. This cosmic preparation is a story of immense time, silent pressure, and the graceful dance of atomic particles, all orchestrated by the fundamental laws of the universe. At its very core, our universe began with elegant simplicity, largely composed of just 2 elements, hydrogen and helium. Hydrogen, the lightest and most abundant element, is the foundational building block for nearly everything we observe, from the smallest atom to the largest galaxy. Picture vast, serene clouds of these primordial gases, spread across the nascent universe like an ethereal mist, almost imperceptible in its quiet diffusion. For countless eons, these gases simply existed, slowly moving, slowly cooling after the initial intensity of the Big Bang. Over immense stretches of time, gravity, that gentle, invisible hand, began to gather these wisps of gas and dust. Slowly, patiently, these diffuse clouds began to coalesce, to draw inward upon themselves, like morning fog slowly concentrating into denser patches over a calm lake. This gentle inward pull led to the formation of denser pockets, like eddies in a vast, calm ocean, or perhaps soft, growing knots in an immense flowing tapestry. As these pockets grew in size and mass, the gravitational forces within them intensified, drawing more and more material closer together with a quiet, persistent tug. This gradual process, unfolding over many millions of years, eventually led to the birth of stars. Imagine a nebula, a colossal cloud of gas and dust, perhaps light years across, so vast that light itself would take years to traverse its quiet depths. Within its serene expanse, tiny fluctuations in density, almost imperceptible ripples, start to grow. Particles, no larger than microscopic grains of cosmic sand, begin to nudge each other, slowly gathering into slightly larger clumps. This accretion process continues, quietly, relentlessly, as gravity works its magic, drawing disparate atoms into a shared destiny until a significant mass is accumulated at the center of this collapsing cloud. At the heart of such a gathering, as billions upon billions of atoms are pressed ever closer, the pressure becomes truly immense, and the temperature begins to rise dramatically. This is the birth of a protostar, a glowing, warm core, radiating a soft, gentle heat. Not yet a true star, but a quiet promise of one. It shines faintly, sustained by the energy of its own gravitational collapse. As it continues to contract and heat, a critical threshold is eventually reached. The temperature and pressure at its core become so extreme that hydrogen atoms begin to overcome their natural electrical repulsion. They are squeezed together with such force that they fuse, combining to form helium. This profound process, known as nuclear fusion, releases an extraordinary amount of energy, marking the true ignition of a star. With this ignition, a true star is born. It shines with a steady, gentle light, a new, warm beacon in the cosmic dark, patiently burning its hydrogen fuel. These stars, vast and radiant, are not merely sources of light and heat that illuminate the cosmic night. They are the universe's silent alchemists, the patient architects of complexity, quietly working their transformations over eons. Within their incredibly hot and dense cores, hydrogen fusion continues, creating helium. But in larger, more massive stars, this process does not stop there. The journey of creation continues. Once the primary hydrogen fuel in the core begins to deplete, gravity once again takes hold, causing the core to contract further and heat up even more. This increased heat and pressure allows new fusion reactions to begin. Helium atoms, themselves the product of earlier fusion, now start to fuse together, combining to form heavier elements like carbon and oxygen. Imagine these essential elements, the very building blocks of life, being quietly forged layer by layer within the star's fiery heart, much like geological strata forming deep within a planet. Each layer a testament to immense pressure and time. As a star nears the end of its magnificent life cycle, especially a massive one, it continues this process of nucleosynthesis, slowly building up even heavier elements through successive fusion stages. Carbon fuses to form neon. Neon in turn forms oxygen and magnesium, and so on, progressing steadily up the periodic table until its core is eventually composed of iron. These elements, essential for the formation of rocky planets, and indeed for life itself, are patiently created over billions of years, a profound cosmic inheritance. When these magnificent, colossal stars finally exhaust their nuclear fuel, they face different, often dramatic, yet ultimately beneficial fates. Smaller stars, much like our own sun, gently expand into luminous red giants, eventually shedding their outer layers in a graceful, expanding puff of gas, leaving behind a compact, cooling white dwarf like a spent ember. But the most massive stars, those many times larger than our sun, end their lives in a far more spectacular, yet profoundly generous way. These stellar giants, having forged elements all the way up to iron in their cores, can no longer sustain themselves against the relentless inward pull of gravity. Their cores collapse inward with astonishing speed and force, leading to a spectacular event known as a supernova. Picture an immense cosmic flower, blooming brightly for a brief, glorious moment, illuminating an entire galaxy, before dispersing its precious seeds across the vast void of space. During this cataclysmic explosion, the forces are so extreme, the temperatures and pressures so immense, that even heavier elements, those beyond iron on the periodic table, are forged in a fleeting instant of unimaginable power. Elements like gold, silver, uranium, and all the precious heavy metals we find on Earth, the very materials that form the foundations of our technology and adorn our lives, owe their existence to these profound, distant explosions. The supernova then scatters these newly created elements, along with the lighter ones forged earlier in the star's more tranquil life, out into the surrounding interstellar space, enriching the cosmic tapestry. This cosmic scattering is incredibly significant. It is the mechanism by which the universe recycles and enriches itself. It provides the next generation of gas and dust clouds, the raw material for new stars and planets, with a richer, more diverse set of building blocks. Imagine these heavier elements, now gently drifting through the cosmic currents, like unseen rivers flowing through space, carrying their precious cargo. They become the vital ingredients for the next cycle of star formation, but with a crucial difference from the first generation of stars. These new stellar nurseries are now seeded with an abundance of carbon, oxygen, nitrogen, and a host of other elements that were entirely absent in the universe's earliest, simpler days. These are the elements that make chemical complexity possible. It is these elements, especially carbon, oxygen, and nitrogen, along with hydrogen, that form the very backbone of life as we understand it. Carbon's unique ability to form long, stable chains and intricate ring structures makes it the ideal atomic scaffolding for complex organic molecules. It is the ultimate connector, able to bond with many other elements in diverse ways, creating the vast variety of molecular shapes necessary for biological function. Oxygen, a reactive and abundant element, is crucial for many biological processes, from the efficient energy extraction in respiration to the formation of water, which is itself the universal solvent for life, providing the medium in which all these chemical reactions can take place. Nitrogen is a key component of proteins, the workhorses of biological systems, and nucleic acids, the very molecules that carry and transmit genetic information from one generation to the next. Without the patient, persistent work of countless generations of stars, stretching back billions of years, these essential building blocks would simply not exist in the quantities necessary for life to emerge. The universe, in a deeply profound sense, literally cooked the ingredients for life in its vast, fiery kitchens, patiently preparing the stage. Now, let us gently shift our focus from the stellar forge to the quiet cradles where planets are born. After a new star has formed, Often a significant amount of gas and dust remains, swirling around it in a flattened, pancake-like disk, much like the gentle rings around a distant planet, but on a vastly larger scale. This is called a protoplanetary disk. Imagine it as a vast, slowly rotating cosmic platter, many billions of miles across, composed of leftover stellar material, now enriched with all those heavy elements forged in supernovae. This disk is not uniformly smooth. It contains subtle variations in density, little swirls and eddies within its quiet, majestic flow. Within this quiet, spinning disk, the process of planet formation begins. It is a subtle and gradual dance, unfolding over tens of millions of years, a geological timescale that dwarfs human experience. Tiny particles of dust, no larger than the finest smoke, gently collide with one another. Because of electrostatic forces, similar to the static cling you might feel in everyday life, they sometimes stick together, forming slightly larger clumps. Picture microscopic snowflakes slowly adhering to each other, gradually growing in size through these soft, feather-light collisions. This process, known as accretion, is incredibly patient and surprisingly gentle at first. Over vast stretches of time, these tiny clumps grow into pebble-sized grains, then into rocks, and then into boulders, each a small world slowly gathering its companions. Gravity, once again, begins to play an increasingly important role as these objects grow in mass. Once a clump reaches a certain size, perhaps a few miles across, its own gravitational pull becomes strong enough to attract other nearby particles more effectively, sweeping them up into its orbit. These growing bodies are called planetesimals, literally tiny planets. They slowly sweep up material in their orbital paths, clearing out lanes within the protoplanetary disk, like a quiet broom gently tidying a dusty floor. Imagine these planetesimals as quiet snowplows, moving through a vast, soft field of cosmic material, gathering everything in their path, slowly increasing their girth and influence. Eventually, these planetesimals themselves collide and merge, often in surprisingly gentle impacts over millions of years, forming even larger bodies called protoplanets. These protoplanets are the nascent worlds, still hot and molten from the immense energy of their formation and the decay of radioactive elements within their cores, gently radiating warmth into the cold darkness of space. Over additional millions of years, these protoplanets continue to grow, to differentiate into distinct layers, forming a core, a mantle, and a crust. This entire process, from the first gentle collisions of dust to the formation of fully fledged planets, is a testament to the universe's quiet, persistent capacity for self-organization, for creating intricate structures from simple beginnings. It creates vast, tranquil spaces where conditions might just be right for something truly remarkable to begin. Our own solar system, with its 8 planets gently orbiting the Sun, each tracing its predictable path through the cosmic void, is a beautiful example of this patient, cosmic craftsmanship. Each planet, a unique world, formed from the same elemental dust, yet developing its own distinct character over billions of years, a testament to the subtle variations in their birth and subsequent evolution. As we contemplate these newly formed worlds, perhaps orbiting distant stars, or even existing within the quieter reaches of our own stellar neighborhood, a profound question naturally arises: what, precisely, are we looking for? How do we define lives in a universal context, beyond the familiar, vibrant forms we see here on Earth? Scientists have grappled with this question for generations, striving for a definition that is broad enough to encompass possibilities we haven't yet imagined, yet specific enough to guide our search through the vastness of space. Rather than focusing on specific chemistries, like the precise structure of DNA or the particular proteins that make up Earth life, we tend to define life by its fundamental processes and behaviors. Imagine a distant world, a quiet, swirling blue marble, or perhaps a muted, rusty red one. If we were to observe it over immense stretches of time, what patterns, what activities might subtly suggest the presence of living things? One of the most essential characteristics we consider is metabolism. This refers to the ability of an organism to take in energy and raw materials from its environment, process them to sustain itself, grow, and then expel waste products. Think of it as a gentle internal hum, a continuous cycle of intake and output, a steady flow of energy and matter, allowing the organism to actively maintain itself against the natural tendency towards disorder and decay. On Earth, this can range from a tiny plant quietly converting sunlight into sugars, a process of serene transformation, to a bacterium consuming minerals in a deep-sea vent, patiently extracting energy from its surroundings. It is the ability to maintain an internal order, to regulate its own chemistry in a quiet, persistent, self-sustaining way. Another crucial attribute is reproduction. Life, by its very nature, creates copies of itself, passing on its information to the next generation. This isn't necessarily about familiar reproduction as we know it, with seeds or offspring, but rather the fundamental ability to make more of itself, to perpetuate its patterns and structures through time. It's a quiet echo across generations, ensuring the continuation of its form and function, a subtle thread connecting past to future. This could be as simple as a single cell gently dividing into two, or as complex as a multicellular organism giving birth. The essence is the faithful, yet adaptable, transfer of self-organizing information. This ability to copy, to propagate, is what allows life to endure and spread. Closely linked to reproduction, and indeed to life's persistence, is growth and development. Living things typically grow over time, increasing in size or complexity, and often undergo a series of predictable changes throughout their lifespan, following an inherent program. Imagine a tiny seed gently swelling and sending down fragile roots into the soil, slowly drawing sustenance and growing larger, or a microscopic organism slowly accumulating mass and differentiating its internal structures. This is the quiet unfolding of an inherent blueprint, a predetermined path of change and maturation, guided by the information it carries. Perhaps one of the most compelling characteristics for identifying alien life is adaptation and evolution. This is the profound capacity for a population of organisms to change over generations in response to their environment. It's a slow, patient molding, like water gently shaping a stone over millennia, subtly refining its form to better suit the currents. If an environment shifts, if conditions subtly alter, life finds a way to adjust, to subtly alter its strategies to survive and thrive. This relentless, quiet process of trial and error, of slight modifications accumulating over vast stretches of time, generation after generation, is what allows life to persist and diversify in a constantly changing universe. It is the signature of life's profound resilience, its quiet determination to endure, to find a way to thrive in new circumstances. This adaptive capacity is a deep, fundamental aspect of life's presence. Finally, most forms of life exhibit homeostasis, the ability to maintain a stable internal environment despite external fluctuations. Think of how a warm-blooded animal maintains its body temperature, or how a single cell regulates its internal chemistry, keeping conditions within a narrow, life-sustaining range, even as the outside world changes dramatically. This is a gentle, internal balancing act, a subtle self-regulation that keeps the delicate machinery of life functioning smoothly, preventing internal chaos and allowing for continuous, organized activity. When we combine these attributes, metabolism, reproduction, growth, adaptation, and homeostasis, we arrive at a robust yet flexible working definition for life beyond Earth. We are not looking for specific alien plants or animals that look like something familiar, but for any system, regardless of its specific chemical basis, that exhibits these fundamental, persistent, and self-organizing qualities. The quest is for patterns of information that can sustain and perpetuate themselves in a universe that otherwise tends towards increasing disorder, a universe where complexity is hard won. It is a search for self-sustaining order in the quiet chaos of space, a glimmer of persistent organization. Now, with these universal characteristics in mind, let us gently turn our gaze to our own homeworld, Earth, during its infancy. Earth stands as our singular, precious example of a planet where life did indeed emerge, transforming its surface and atmosphere profoundly. Its early history offers a poignant and perhaps common blueprint for life's mysterious stirrings, a quiet testament to the possible pathways life might take elsewhere. Imagine early Earth, not as the vibrant blue and green planet we know today, teeming with diverse life, but as a more subdued world, perhaps a gentle swirl of muted greens and browns under a hazy, often cloud-covered sky, with a distinctly unfamiliar silence. During its first billion years or so, known as the Hadean and Archean eons, Earth was a very different place. Its atmosphere was vastly different from our oxygen-rich air, completely devoid of free oxygen. Instead, it was rich in gases like methane, ammonia, water vapor, and carbon dioxide, gases quietly released by volcanic activity. Picture this primordial atmosphere as a thick, anoxic blanket, gently diffusing the sunlight, filtering its rays, creating a muted, almost dreamlike landscape. The air would have felt heavy, perhaps a little warm from ongoing volcanic activity and the planet's internal heat, but silent in its chemical composition, utterly unlike the breathable air we now take for granted. Beneath this atmosphere lay vast, warm, primordial oceans. These weren't the teeming, bustling oceans we know today, filled with whales, fish, and coral reefs, but rather quiet, expansive bodies of water, perhaps shallower in places, filled with a rich broth of dissolved minerals and organic molecules. Imagine the gentle lapping of waves against barren, rocky shores, with no sound of birds or complex creatures, only the timeless murmur of water meeting stone. The water itself would have been a calm, chemical soup, a vast crucible where the most fundamental ingredients for life were slowly, patiently mixed, interacting under the influence of various energy sources. Geological activity was intense during this period, constantly shaping the young planet. Volcanoes would have quietly belched gases and lava, adding to the atmosphere and enriching the oceans with new minerals, a continuous geological process. Hot hydrothermal vents, deep beneath the ocean's surface, where tectonic plates slowly pull apart, would have continuously streamed mineral-rich, superheated water into the vast depths. These vents, still active today in places like the Pacific Ocean, provide warm, chemically vibrant microenvironments, often considered prime candidates for the very origins of life. Imagine the silent, consistent flow of these mineral-rich waters, creating intricate chemical reactions in the utter darkness, a hidden world of chemical potential, far from the sun's surface rays. It was in this serene, yet chemically active environment that the slow stirring of nascent life is thought to have begun. Picture simple organic molecules, the very carbon-based compounds that form the building blocks of life, perhaps delivered by comets and meteorites from space, which gently showered the early Earth, or formed right here on Earth through the gentle action of lightning discharges in the atmosphere, or the intense heat from volcanic activity. These molecules, the basic building blocks like amino acids, which make proteins, and nucleotides, which make DNA and RNA, would have dissolved in the warm primordial oceans, mingling and interacting. Over immense stretches of time, perhaps hundreds of millions of years, these simple molecules began to self-assemble into more complex structures. Imagine them gently bumping into each other, forming longer chains, like beads slowly strung together, perhaps adhering to the surfaces of clay minerals, which could have acted as quiet templates or catalysts, organizing these molecules into more complex patterns. The earliest forms of life were not complex organisms with recognizable features, but perhaps self-replicating molecules, such as early forms of RNA, capable of making copies of themselves, however imperfectly. This was the quiet dawn of information, the moment when chemical patterns began to persist and multiply, passing their blueprints forward. These early proto-life forms would have been incredibly simple, perhaps just tiny packets of self-replicating molecules enclosed within a primitive membrane, a quiet, permeable boundary separating their internal chemistry from the vast external ocean around them. They would have existed in a profound, delicate balance with their environment, gently drawing sustenance from the surrounding chemical soup, slowly evolving the ability to more efficiently capture energy and reproduce. And so, slowly, patiently, evolving the fundamental processes that define life. The emergence of the first true cells, single-celled organisms with more robust membranes and internal machinery, was a monumental step, but it was a step taken over immense spans of time, a slow, quiet unfolding of biological possibility, culminating in the ancestors of all life we see around us today. The story of early Earth is a testament to the universe's patient capacity for life. It shows that given the right raw materials, energy, and a long, stable environment, the quiet, persistent forces of chemistry and physics can give rise to something truly extraordinary. It is a blueprint that we carry with us as we look out into the quiet, starlit night, wondering if similar cradles exist elsewhere, patiently nurturing their own unique forms of life, awaiting our gentle, curious gaze. The universe is vast and old, and its capacity for wonder, for life, for creation seems to be boundless. We drift quietly through its immense story, ever searching, ever learning. As we float further into this vast topic, unveiling habitable worlds, close to home and far beyond, our search for life naturally guides us to places where conditions might allow it to thrive, not just in some far-off distant galaxy, but within the quiet confines of our own stellar neighborhood, and in the vast, peaceful reaches beyond. Imagine, for a moment, resting softly in the silent dark, gazing at a star, and pondering the delicate balance required for a world to harbor liquid water on its surface. This is where our gentle exploration of habitable worlds begins, with a principle affectionately known as the Goldilocks principle. This principle suggests that for a planet to potentially support life as we understand it, it needs to orbit its star at just the right distance. Not too close, where the star's radiant energy would boil away any surface water, turning the planet into a scorching, arid wasteland, its atmosphere perhaps stripped away over eons by the star's relentless winds. And not too far, where the star's warmth would be too weak, leaving any water frozen solid in a perpetual icy grip, a world locked in the embrace of eternal winter. The ideal distance creates a zone where temperatures are just right, for liquid water to exist stably on a planet's surface. Picture a comfortable warmth radiating outwards from a gentle fire on a cool evening, a soft, inviting glow. There is a sweet spot, a perfect distance, where you feel neither too hot nor too cold, but simply comfortable and at ease. This is the stellar habitable zone, often visualized as a serene, invisible ring around a star. A quiet promise of warmth and fluidity, a potential cradle for life. The precise location and width of this habitable zone depend entirely on the nature of the star itself, a silent ballet of stellar physics. A brighter, more massive star, burning hotter and more intensely, will have a wider habitable zone located much farther away from its blazing core. Its fierce, luminous light creates a broader band of warmth, extending its nurturing influence across a wider swath of space. Conversely, a smaller, cooler star, like a red dwarf, which radiates far less energy, will have a much narrower habitable zone, drawn in much closer to its dimmer, often reddish glow. These cooler, less luminous stars, though seemingly less hospitable, are incredibly numerous in our galaxy, gently dotting the cosmic landscape like countless, faint embers. Their immense longevity, lasting for trillions of years, far longer than stars like our Sun, offers a vast canvas of time for life to potentially emerge and evolve within their snug, close-in habitable zones. This extended period of stability could be a profound advantage, allowing life to slowly unfold without the dramatic stellar changes that might affect shorter-lived stars. However, the presence of liquid water on a planet's surface is not the only factor in this intricate cosmic equation. A world's atmosphere plays a crucial, dynamic role, acting like a gentle, protective blanket, regulating temperature and shielding against radiation. A thick atmosphere, particularly one rich in greenhouse gases like carbon dioxide and water vapor, can trap heat, much like a cozy duvet, extending the outer boundary of the habitable zone, allowing liquid water to persist even a little farther from the star. This atmospheric embrace can gently warm a distant world, keeping its oceans from freezing entirely. Conversely, a very thin atmosphere, or one entirely absent, might allow too much heat to escape into space, effectively shrinking the habitable zone inward, leaving a world exposed and vulnerable to extreme temperature swings. Consider Earth's atmosphere, a delicate, life-sustaining veil that keeps our planet warm enough to sustain its oceans and vibrant ecosystems, protecting us from the harsh vacuum of space and the sun's raw, unfiltered energy. It's a subtle, ongoing interplay of stellar warmth, planetary composition, and atmospheric embrace, creating a temperate haven, a quiet equilibrium that allows life to flourish. The concept of the habitable zone, initially focused primarily on surface liquid water, has expanded significantly in recent decades, nurtured by new discoveries. The more we learn about the astonishing resilience and adaptability of life on Earth, especially extremophiles thriving in environments once thought utterly impossible, the more our understanding of habitable grows and deepens. We've realized that the gentle, direct warmth of a central star isn't the only way to keep water liquid. Sometimes, The universe offers other, more subtle, internal heating mechanisms, creating hidden oases in unexpected places, worlds that defy our initial assumptions. This leads us to consider worlds where liquid water might exist, not on the surface, exposed to the harsh vacuum of space, but deep beneath protective layers of ice or rock, warmed by the quiet, persistent forces originating from within the planet itself. These are the truly fascinating possibilities, challenging us to look beyond the obvious, to peer into the hidden depths of cosmic potential. Imagine a world far, far from the comforting warmth of its parent star, seemingly frozen solid, a quiet, icy sphere drifting in the cold expanse, yet harboring a hidden warmth, a secret ocean in its core. How might such an unlikely sanctuary be maintained, away from the life-giving light of a star? The answer often lies in the powerful, yet silent, dance of gravitational forces between a moon and its colossal planetary host. This phenomenon is particularly true for moons orbiting giant planets, locked in a perpetual, graceful cosmic embrace. This is known as tidal heating. Consider a moon gently orbiting a massive gas giant, like the majestic Jupiter or the serene Saturn. As the moon draws closer to the planet in its elliptical orbit, the planet's immense gravity pulls more strongly on the moon's near side than on its far side, subtly stretching the moon into a slightly elongated, egg-like shape. Then, as the moon moves farther away in its orbit, the gravitational pull lessens, and the moon relaxes back into a more spherical form. This continuous stretching and relaxing, this gentle, internal cosmic kneading, generates friction within the moon's interior. This friction, over immense timescales, similar to flexing a thick piece of metal back and forth until it warms, manifests as heat, a steady internal warmth radiating from the core outwards. Picture a rubber ball being gently but persistently squeezed and released over and over again. After a while, you would feel a subtle warmth developing within it. The same principle, writ large across cosmic distances and amplified by the immense masses involved, generates enough heat to melt vast quantities of ice, creating hidden, subsurface oceans that could persist for billions of years, patiently waiting in the dark. These internal heat sources are profound game changers in our hunt for alien life. They liberate worlds from the strict confines of the stellar habitable zone, allowing liquid water to thrive in places that would otherwise be perpetually frozen, cold, and utterly lifeless. This expansion of habitability means that the universe might be far more generous with its life-sustaining environments than we initially imagined, opening up entirely new frontiers for exploration. It suggests that even in the frigid outer reaches of a star system, where sunlight is but a faint glimmer, a distant memory, life might find a quiet refuge, nurtured by the invisible hand of gravity and the gentle warmth of internal friction. This revelation has truly transformed our perspective, guiding our gaze inward towards the surprising and often hidden ocean worlds within our own solar system, where liquid water exists in forms and places we once thought impossible, held captive by ice but free to flow. Let us now turn our attention to three of the most intriguing of these ocean worlds, all orbiting the majestic gas giants in our outer solar system, Europa, Enceladus, and Titan. These are not planets themselves, but rather moons, each a unique testament to the diverse ways that liquid environments can be maintained beyond the direct warmth of a star. Each one offers a different, fascinating possibility for life, challenging our preconceived notions of where life might exist, pushing the boundaries of our imagination. First, we will consider Europa, one of Jupiter's large Galilean moons, a world shrouded in a thick shell of ice. Then, we will journey to Enceladus, a much smaller moon orbiting Saturn, famous for its geysers of water. Finally, our exploration will lead us to Titan, Saturn's largest moon, a truly unique world with a thick atmosphere and an entirely different kind of liquid on its surface. These icy moons, seemingly desolate and cold on their exteriors, hide within them the potential for dynamic, liquid environments, proving that appearances can be profoundly deceiving in the cosmos. They are quiet havens, waiting for us to gently peel back their icy veils, to listen for their hidden stories. Let us begin with Europa, a moon of Jupiter that has captivated scientists for decades, a world of elegant simplicity on the surface, yet profound complexity beneath. From a distance, Europa appears as a smooth, almost featureless sphere, pristine and white, but crisscrossed by long, graceful lines, like delicate cracks in a porcelain surface or fine scratches on an ancient, polished stone. It is slightly smaller than Earth's moon, yet it holds a secret that makes it profoundly compelling, a vast, deep ocean of liquid water hidden beneath miles of solid ice. This ocean is thought to contain more water than all of Earth's oceans combined, a staggering volume of liquid, patiently held in its hidden embrace, a true treasure beneath the ice. The evidence for Europa's hidden ocean has accumulated over many years, through meticulous observations from spacecraft like the pioneering Voyager probes and, most importantly, the Galileo mission, which orbited Jupiter from 1995 to 2003. Galileo's instruments delicately measured Europa's magnetic field, revealing a signature consistent with a vast, electrically conductive layer beneath its icy crust. This conductivity strongly indicated the presence of a salty liquid ocean, as saltwater is an excellent conductor of electricity. Furthermore, Europa's surface itself offers subtle clues to the dynamic processes occurring below. The long, linear cracks, some stretching for thousands of miles across its frozen face, suggest a dynamic, flexing crust, consistent with a mobile ocean underneath that can exert stress on the rigid ice shell. Some regions of the ice even look like jumbled icebergs, what scientists call chaos terrain, as if a frozen ocean has broken apart and refrozen in a disordered pattern, a testament to the internal stirring and movement. This vast, dark subsurface ocean on Europa is gently warmed by the very tidal forces we discussed earlier, orchestrated by Jupiter's immense gravity. Jupiter's immense gravitational pull continuously flexes and kneads Europa's interior, generating enough heat to keep the water from freezing solid, despite the moon's immense distance from the sun and the frigid temperatures of space. Imagine a deep, tranquil ocean, perpetually dark, untouched by sunlight, shielded from the harsh radiation of space by miles of solid ice above. This thick ice shell acts as a protective barrier, insulating the ocean and creating an incredibly stable environment, undisturbed by surface weather or cosmic impacts. This stability, coupled with the potential for energy, is crucial for the emergence and persistence of life. Perhaps the most exciting possibility for life within Europa's ocean lies at its seafloor, where the liquid water meets Europa's rocky core. Scientists hypothesize that, similar to Earth's deep-sea environments, Europa's rocky core might be in active contact with its ocean, leading to the formation of hydrothermal vents. On Earth, these vents, often found along mid-ocean ridges, are oases of life, spewing superheated, mineral-rich water from the planet's interior. They create unique ecosystems where life thrives not on sunlight, but on chemical energy, a process called chemosynthesis. Imagine the silent, consistent flow of these vents on Europa, gently releasing warmth and chemical nutrients, like hydrogen sulfide or methane, into the frigid, dark ocean. These vents could provide the energy and the raw chemical ingredients necessary for microbial life to emerge and flourish, completely independent of the distant sun's light. It's a tantalizing vision of a calm, hidden world, teeming with unseen life, a deep, quiet sanctuary. Future missions, such as the Europa Clipper, are designed to conduct numerous close flybys of this enigmatic moon, using advanced radar to gently penetrate the icy shell and map the ocean's depth, salinity, and characteristics with unprecedented detail. Other instruments, like magnetometers and thermal imagers, will meticulously search for signs of active plumes and hotspots, indications of internal activity. They will also analyze any faint plumes of water that might periodically erupt from Europa's surface, similar to those seen on Enceladus, offering us a tantalizing, direct glimpse into the ocean below without the need for complex drilling. The prospect of finding a quiet, undisturbed ecosystem in such an unlikely place fills us with a profound sense of wonder and patience, a quiet anticipation of what might be revealed. Next, let us gently journey further out into the solar system, to the magnificent ringed planet Saturn and one of its smaller, yet equally captivating moons, Enceladus. Discovered in 1789, Enceladus remained largely an enigma, a simple bright dot against the backdrop of Saturn's rings, until the Cassini spacecraft's extensive observations from 2004 to 2017. What Cassini unveiled was nothing short of astonishing, a small icy moon, only about 35 miles, 500 kilometers, across, roughly the size of Arizona, that is incredibly geologically active and dynamic. The most remarkable feature of Enceladus, and what truly sets it apart, is its spectacular plumes of water and organic molecules, constantly erupting from its south polar region. Imagine watching a cosmic geyser, gently exhaling its secrets into space, like soft breaths in the cold vacuum, spraying material hundreds of miles into the void. These plumes, first observed directly by Cassini's instruments, are composed primarily of water vapor, but also contain tiny ice grains, various salts, and even complex organic molecules, the very building blocks of life. Cassini even flew directly through these plumes on multiple occasions, collecting samples of this extraterrestrial spray and providing a direct, invaluable window into the moon's interior chemistry and composition. This was an unprecedented opportunity to taste an alien ocean. The source of these plumes is now understood to be a vast, global subsurface ocean, nestled between Enceladus's icy crust and its rocky core, much like Europa's. The heating mechanism here is again tidal forces, but in this case, the intricate gravitational tugs from Saturn and its other moons, particularly Dione, continually flex Enceladus in a complex dance. This flexing is concentrated along deep fractures in the south polar region, which scientists affectionately call tiger stripes due to their distinctive parallel appearance. These tiger stripes are essentially gateways, thin cracks in the ice, allowing the ocean water, under pressure, to escape as jets and plumes into space, carrying the ocean's secrets with it. The meticulous analysis of the plume material by Cassini has revealed an astonishing chemical richness. It detected not only water and salts, confirming a salty ocean, but also silica nanoparticles, hydrogen gas, methane, and various other complex organic compounds, including those that contain nitrogen. The presence of silica nanoparticles strongly suggests that the ocean water is actively interacting with a rocky seafloor at remarkably high temperatures, around 90 degrees Celsius, 194 degrees Fahrenheit, indicating active hydrothermal vents. The detection of molecular hydrogen, a powerful potential energy source for microbial life, further strengthens the analogy to Earth's deep-sea hydrothermal systems, where specific types of microbes thrive by harnessing chemical reactions far from the sun's light. Imagine a serene, hidden ocean on Enceladus, continuously replenished with chemical energy from its rocky core, a quiet crucible for life sustained by unseen forces. Enceladus provides us with an almost unprecedented opportunity in our quest. The plumes are, in essence, a free sample of an alien ocean, ejected directly into space, bypassing the need for complex drilling through miles of ice. Future missions could potentially fly through these plumes again, perhaps even collecting samples to return to Earth for detailed laboratory analysis, allowing for even more precise investigations without ever needing to land on the moon itself or develop deep drilling technology. The possibility of finding active, chemosynthetic life within this tiny, distant moon is a deeply profound and exciting prospect, transforming our understanding of planetary habitability and the sheer variety of life's potential abodes. It is a world quietly demonstrating that life's potential truly knows no bounds, existing in the most unexpected, tranquil corners of our solar system. Our journey through the outer solar system continues, leading us to another one of Saturn's moons, a world utterly unique and profoundly intriguing. Titan. Titan is Saturn's largest moon, even bigger than the planet Mercury, and it stands apart from Europa and Enceladus in several key ways. Its most striking feature is its thick, hazy, nitrogen-rich atmosphere, which completely obscures its surface from visible light. This atmosphere is rich in nitrogen, much like Earth's, but also contains a significant amount of methane and other complex hydrocarbons, creating a perpetual atmospheric haze. Picture a world perpetually shrouded in a gentle orange-brown haze, diffusing the weak sunlight into a perpetual twilight, a soft, muted glow. Beneath this thick, hazy atmosphere, Titan harbors something truly alien and captivating. Vast lakes and rivers, not of liquid water, but of liquid methane and ethane. At Titan's extremely frigid surface temperatures, around -179 degrees Celsius, -290 degrees Fahrenheit, water ice is as hard and unyielding as rock. But methane and ethane, which are gases on Earth, exist as stable liquids there, forming vast, tranquil bodies. Imagine a landscape with familiar features, gently flowing rivers, calm, reflective lakes, even rain and clouds, but composed of utterly alien fluids, a world where the very chemistry of its liquid environments is fundamentally different from our own. The Huygens probe, which descended through Titan's atmosphere in 2005 as part of the Cassini mission, provided us with our first direct glimpse of this exotic surface. It parachuted slowly through the thick atmosphere, taking pictures and scientific measurements of atmospheric composition, eventually landing softly on a muddy but solid plain near one of the equatorial regions. The images it returned, and the radar mapping by Cassini, revealed a diverse landscape, rugged highlands, vast plains, and extensive dune fields composed of hydrocarbon sands, some reaching hundreds of feet in height. The lakes are concentrated near the poles, reflecting the dim sunlight like liquid mirrors, still and serene. Titan's entire system operates on a methane cycle, wonderfully analogous to Earth's water cycle. Methane evaporates from the lakes and rivers, forms clouds in the atmosphere, and then falls as gentle methane rain, carving channels and filling depressions, replenishing the surface liquids. This is a truly active world, constantly shaped by its alien weather patterns, its slow, persistent geological and meteorological processes. The profound question then naturally arises, could life exist in such an environment so different from Earth? While life as we know it is entirely dependent on liquid water as a solvent, providing the medium for all its complex chemical reactions, the concept of life on Titan challenges us to expand our imagination far beyond our familiar biological paradigm. Could life exist that uses liquid methane or ethane as its solvent rather than water? This would imply a fundamentally different kind of biochemistry, perhaps using different building blocks or operating at vastly different, much colder temperatures. Scientists have even theorized about hypothetical life forms, sometimes referred to as methanogens, though distinct from Earth microbes with that name, which might derive energy from chemical reactions involving hydrocarbons and hydrogen, much like Earth's deep-sea chemosynthetic life thrives in the absence of sunlight. Imagine such life forms quietly metabolizing in Titan's frigid lakes, an entirely new branch on the tree of life, operating under utterly alien principles, a testament to life's potential versatility. Titan presents a profound reminder that our search for life must be open to possibilities beyond merely Earth-like conditions. It encourages us to think creatively and with open minds about the fundamental requirements for life, perhaps moving beyond the strict reliance on liquid water and considering other stable liquid solvents. The existence of such a rich, complex organic chemistry, including the presence of complex organic molecules in Titan's atmosphere and on its surface, points to a world that is not inert, but chemically active, constantly evolving, and full of quiet, unexamined potential. It broadens our cosmic horizons. As we gently conclude this segment, our journey through these habitable worlds, both those close to home and those orbiting distant stars, reveals a universe far richer and more diverse than we once dared to imagine. From the gentle Goldilocks zones around distant stars, precisely balanced to sustain surface water, to the hidden, tidally warmed oceans of Europa and Enceladus, patiently shielded by miles of ice, and even the exotic methane seas of Titan, the cosmos consistently presents us with unexpected sanctuaries for life. The quiet, persistent forces of gravity, geology, and chemistry are at work everywhere, creating conditions that might just allow life to emerge in myriad forms, whether familiar or exquisitely alien. Our understanding of habitability continues to expand, inviting us to contemplate the vast, tranquil possibilities for life's existence, patiently waiting to be unveiled. As we drift deeper into our exploration, listening for life's breath, atmospheric biosignatures from afar, our gentle journey continues as we now turn our gaze from the relatively close confines of our solar system towards the distant, countless stars that dot the velvet expanse of night. Imagine drifting softly in this cosmic ocean, allowing your mind to travel light years away to worlds we cannot yet see directly, but whose quiet presence we can detect through the subtle, unwavering language of light. Here, our instruments become extensions of our senses, patiently listening for life's faint breath, seeking the telltale chemical whispers within the atmospheres of these distant exoplanets. It is a quest that merges the deepest reaches of astrophysics with the enduring human longing to understand our place in the universe. For millennia, humanity could only ponder the existence of planets beyond our sun. They remained elusive, hidden by the overwhelming glare of their parent stars, like tiny fireflies attempting to dance around a brilliant searchlight, their presence utterly swallowed by the immense luminosity. But in recent decades, our ingenuity has unlocked remarkable ways to reveal these hidden worlds. Astronomers, with immense patience and meticulous precision, have developed ingenious methods to detect these exoplanets, even those light years away, nestled in the quiet dark. These methods are like listening for the faint rustle of leaves in a far-off forest, almost beyond the edge of hearing, or feeling the subtle, rhythmic vibration of a distant, hidden bell, whose source remains unseen. Each discovery is a gentle lifting of the cosmic veil, revealing more of the universe's quiet complexity. One of the primary ways we gently uncover these distant worlds is through a technique known as the transit method. Imagine a quiet, serene ballet in space, where a planet gracefully orbits its star. If that planet's orbital path happens to align precisely with our line of sight from Earth, then, at regular intervals, the planet will pass directly in front of its star. From our vantage point, the distant star will appear to dim ever so slightly, for a brief, predictable period. Picture a tiny, silent moth fluttering across the face of a distant lantern, momentarily reducing its brightness, or a minuscule shadow passing over a luminous orb. This subtle dimming is incredibly faint, often just a fraction of a percent, or even 1,000th of a percent, of the star's total light. The reason for such a small change lies in the immense size difference between a star and its orbiting planet. Even a gas giant like Jupiter is only about 1/10 the diameter of our Sun, and an Earth-sized planet is far smaller still. Yet, our sensitive telescopes, patiently gathering light over hours and even days, can detect this minute change with astounding accuracy. As the planet begins its transit, the star's light gently decreases, typically over a period of minutes or hours, creating a smooth downward slope in the measured brightness. It then holds at this lowered brightness for a few hours, depending on the planet's size and orbital speed, before gradually returning to its original luminosity as the planet completes its passage. The amount of dimming tells us about the size of the planet relative to its star, while the regularity of these dips reveals the planet's orbital period, much like the rhythmic, consistent ticking of a cosmic clock. For a world to be confirmed as a planet, we must observe at least 3 such transits, patiently waiting for the quiet, repeated pattern to emerge reliably from the stellar glow, confirming it is not just random stellar activity. This method works best for larger planets, orbiting relatively close to their stars, as they cause more noticeable dips and transit more frequently, making them easier to spot in the vastness. The other foundational method for discovering exoplanets is called the radial velocity method, sometimes affectionately known as the stellar wobble technique. This method relies on the fundamental principle of gravity. Stars do not simply sit perfectly still while planets orbit them. Instead, both the star and the planet are gently pulling on each other, orbiting around a common center of mass, a point in space that represents their combined gravitational equilibrium. Imagine 2 dancers gracefully circling each other, not around one stationary center, but around an invisible point between them. A planet, even a small one, will exert a subtle gravitational tug on its much larger star, causing the star to respond with a tiny, reciprocal movement. Imagine a large, calm boat being subtly, rhythmically nudged back and forth by a smaller, unseen dinghy tied to it, causing a gentle oscillation. This gravitational tug causes the star to gently wobble, moving ever so slightly towards us and then away from us. We cannot directly see this minute wobble, but we can detect its effect on the star's light through something called the Doppler effect. Just as the pitch of an ambulance siren changes as it moves towards or away from you, the wavelength of light also shifts. As the star gently moves towards Earth, its light waves are slightly compressed, appearing to shift towards the bluer, shorter wavelength end of the spectrum. As it gently moves away, its light waves are slightly stretched, appearing to shift towards the redder, longer wavelength end of the spectrum. This blue shift and red shift of the starlight is incredibly subtle, sometimes representing shifts in velocity no greater than a slow walk. Detecting these tiny shifts requires highly precise instruments called spectrographs, which can meticulously analyze the colors within the star's light, separating them into an incredibly detailed rainbow. By patiently observing these minute rhythmic shifts in the star's spectrum over many months or even years, astronomers can infer the presence of an unseen planet. The larger the wobble, meaning the greater the shift in the star's velocity, the more massive the planet or the closer it orbits its star, as these factors lead to stronger gravitational tugs. The period of the wobble reveals the planet's orbital period. This method has been particularly successful at finding massive planets, often gas giants like Jupiter, orbiting relatively close to their stars due to their stronger gravitational influence and shorter orbital periods. Both the transit and radial velocity methods are complementary, each offering unique insights and often confirming each other's discoveries, painting an ever richer, more detailed picture of the universe's planetary tapestry, one subtle movement at a time. The sheer scale of exoplanet discoveries since the mid-1990s has been nothing short of astonishing, painting a vivid picture of a universe teeming with diverse worlds. From just a handful of confirmed exoplanets 3 decades ago, we have now confirmed over 5,000, with many thousands more awaiting confirmation from ongoing missions like the Kepler and TESS space telescopes. These discoveries have profoundly transformed our cosmic perspective, moving us from a view of our solar system as potentially unique to one where planets are seemingly ubiquitous, a common byproduct of star formation. Imagine each star in the night sky as a potential sun, quietly orbited by its own retinue of worlds, some perhaps similar to Earth, some utterly alien, all patiently following their cosmic paths. These discoveries reveal an incredible diversity of planetary types, far beyond the familiar rocky inner worlds and gas giants of our own solar system. We have found hot Jupiters, gas giants orbiting incredibly close to their stars, seared by intense heat, completing an orbit in mere days. We have found super-Earths, rocky worlds larger than Earth but smaller than Neptune, a class of planet not found in our own solar system, offering new insights into planetary formation. We have found mini-Neptunes, worlds smaller than Neptune but with thick, hydrogen-rich atmospheres, as well as lava worlds where rock itself might flow like liquid on the surface due to extreme heat. This vast cosmic zoo of planetary types reminds us that nature's imagination far exceeds our own, and that the universe is far more inventive than we could have ever conceived. It tells us that planet formation is not a rare event, but a quiet, commonplace process throughout the galaxy, almost an inevitable consequence of stellar birth. This abundance profoundly strengthens the argument that life might indeed be widespread. If planets are everywhere, then the opportunities for life to emerge in various forms are far more numerous than we once conceived, making our search a hopeful endeavor across a boundless, quiet expanse. Now, having learned how to gently detect these distant worlds, the next profound step in our quiet quest for life is to examine their atmospheres. This is where the subtle whispers of potential biology might reside, etched into the very light that filters through alien air. The science we employ for this delicate task is called atmospheric spectroscopy. Imagine gently taking a beam of starlight and carefully unfurling it into a cosmic rainbow, a spectrum of all its constituent colors, from deep violet to crimson red. Then, patiently, with meticulous attention, we look for tiny, dark lines or bright spikes within that rainbow, each one a unique calling card from the elements and molecules present in the planet's atmosphere. The principle behind spectroscopy is elegantly simple, yet incredibly powerful in its application across vast distances. When light passes through a gas, the energy in the light interacts with the electrons and atoms within the molecules of that gas. Depending on the specific molecular structure, certain wavelengths or colors of that light are absorbed by the molecules, causing their electrons to jump to higher energy levels or their bonds to vibrate in specific ways. Each type of molecule, be it water, carbon dioxide, oxygen or methane, has a unique pattern of absorption, like a distinct musical chord that it sings when light passes through it, or a unique fingerprint left upon the light itself. Other molecules might emit light at specific wavelengths when heated, adding bright lines to the spectrum. By analyzing these subtle absorption or emission features in the starlight, which appear as dips or peaks in the light spectrum, we can deduce the chemical composition of the exoplanet's atmosphere. It is like reading a unique chemical fingerprint left by the passing light, a silent testimony to the gases present in the air of a world light years away. To achieve this for an exoplanet, we typically use the transit method once more, combining our observational techniques. As a planet passes in front of its star, a tiny fraction of the starlight filters through the planet's atmosphere, grazing its upper layers before continuing its long journey to our telescopes. During this brief passage, the atmospheric gases absorb some of the starlight at their characteristic wavelengths, leaving their subtle mark. By carefully comparing the spectrum of the star's light when the planet is not transiting to the spectrum when it is transiting, we can isolate the absorption signature of the planet's atmosphere. Imagine two nearly identical serene paintings, side by side, and then one has a few brushstrokes subtly altered, almost imperceptibly. By meticulously comparing them, you can discern those tiny, telling differences, revealing the hidden details. This different spectrum, though incredibly faint, holds the secrets of the alien air. This technique, known as transmission spectroscopy, allows us to literally taste the atmosphere of a world light years away, chemically analyzing its breath from across the cosmic abyss. It is a slow, patient process of gathering every photon, every tiny packet of light, to piece together a coherent, compelling picture of a distant world's atmospheric makeup. This ability to chemically analyze exoplanet atmospheres opens a breathtaking window into the potential for life beyond Earth. We are no longer just looking for rocks and gas, or inferring a planet's size and orbit, but for the very breath of a living world, the subtle exhalations of its biology. This brings us to the core of our search for biosignatures, gases in an exoplanet's atmosphere that are present in quantities or combinations that strongly suggest biological rather than purely geological or atmospheric processes. These are the chemical whispers of life from afar, subtle hints across the cosmic expanse, inviting us to ponder their origins. One of the most powerful and eagerly sought biosignatures is oxygen, particularly in its molecular form, O2. On Earth, the vast majority of free molecular oxygen in our atmosphere is produced by photosynthesis, the process by which plants and cyanobacteria quietly convert sunlight into energy, releasing oxygen as a waste product. Oxygen is highly reactive. It readily combines with rocks, minerals, and other elements, without a constant biological source actively pumping it into the atmosphere. Earth's oxygen-rich atmosphere would quickly disappear, reacting away in perhaps only a few million years. So, finding significant amounts of free oxygen in a distant exoplanet's atmosphere would be a deeply compelling sign of active biological processes. Imagine a distant world shimmering with a blue glow, and within its atmosphere, the quiet, persistent signature of oxygen continuously replenished by unseen biological engines, a silent testament to life's pervasive work. However, oxygen alone is not a definitive, unquestionable proof of life. This is where scientific caution and meticulous investigation become paramount. There are theoretical abiotic, or non-biological, processes that could produce small amounts of free oxygen. For instance, intense ultraviolet light from a star could break down water vapor, FAR, H2O, into hydrogen and oxygen. If the lighter hydrogen then escapes to space, leaving the heavier oxygen behind, a non-biological accumulation of O2 could occur. This is why context is so vital in our search. It is not just the presence of a single gas, but its concentration, and more importantly, its coexistence with other gases, that paints a more complete, unambiguous picture. A true biosignature is rarely a solitary chemical, but rather a harmonious ensemble of gases that collectively defies a purely geological explanation, a subtle symphony of chemicals. This leads us to consider another crucial potential biosignature, methane, CH4. Methane is also produced by life on Earth, primarily by microbes in anaerobic environments, those lacking oxygen, such as wetlands, the digestive tracts of animals, or deep within sediments. But like oxygen, methane can also be produced by geological processes, such as volcanism or serpentinization, which is the alteration of specific rocks by the interaction with water. What makes methane particularly interesting as a biosignature is its reactivity. Methane is rapidly destroyed by ultraviolet light in a star's atmosphere, with a relatively short atmospheric lifespan. So, if we were to detect significant amounts of methane in an exoplanet's atmosphere, it would imply that there must be a constant, active source replenishing it. If this continuous replenishment cannot be adequately explained by geological processes, then a powerful biological source becomes a compelling, even exciting possibility. Picture a gentle, invisible plume of methane being quietly exhaled by unseen life forms, continuously countering the forces that seek to break it down, maintaining a delicate chemical balance. When oxygen and methane are found together in significant, unexplainable quantities, it becomes an even more potent and convincing biosignature. On Earth, these two gases are largely incompatible. Oxygen actively destroys methane. Their simultaneous presence in high concentrations, particularly if carbon dioxide is also present in low amounts, suggests an active, powerful biological engine constantly producing both gases, maintaining a state of profound chemical disequilibrium. This disequilibrium, this chemical imbalance, is difficult to explain through purely geological means over long timescales. It suggests an active, living system is working to maintain this imbalance, much like a gardener patiently tends to a garden, constantly battling natural processes to maintain order. Imagine a serene, distant world where a delicate chemical dance is maintained, not by random chance, but by the quiet, persistent activity of living things, their presence subtly altering the very composition of their home. Closely related to oxygen is ozone, O3. Ozone is formed when ultraviolet light from a star interacts with molecular oxygen in a planet's upper atmosphere, transforming O2 into O3. If we detect ozone, it serves as an indirect but strong indicator of the presence of molecular oxygen below it. Since ozone absorbs different wavelengths of light than molecular oxygen, and often at stronger, more easily detectable features, it can sometimes be easier to detect, especially in certain atmospheric conditions or at specific altitudes. So, finding ozone might be like hearing a quiet echo of oxygen's presence, a subtle confirmation from the upper atmosphere, a more easily caught whisper. Other potential biosignatures include nitrous oxide, ammonia, and even phosphine, each presenting their own unique set of challenges and interpretative nuances. For example, phosphine was controversially reported in the atmosphere of Venus, highlighting the extreme difficulty and the need for meticulous verification when seeking such faint chemical clues. Such detections demand immense patience, careful calibration, and a deep understanding of all possible non-biological sources. The immense patience and precision required to detect these incredibly faint signals across cosmic distances cannot be overstated. We are, in essence, listening for a whisper in a silent, vast hall, trying to discern a tiny, specific melody amidst the universe's natural hum. The light from these distant exoplanets is incredibly dim, having arrived at Earth after traveling for centuries or even millennia. Each photon, each tiny packet of light, must be carefully collected and analyzed, like painstakingly sifting through vast quantities of cosmic dust for precious, glittering grains, each one carrying a piece of the puzzle. This delicate search demands instruments of unprecedented capability, a task now being spearheaded by next-generation space telescopes. The James Webb Space Telescope, or JWST, is at the forefront of this endeavor. Launched in 2021, JWST is primarily an infrared observatory, meaning it specializes in detecting infrared light, the very heat emitted by objects in space. This is crucial for exoplanet atmospheric studies, because many biosignature gases, like methane, carbon dioxide, and water vapor, absorb strongly in the infrared part of the spectrum. Additionally, cooler, smaller stars, like red dwarfs, which have many potentially habitable planets, emit much of their light in the infrared, making JWST perfectly suited to study their systems with greater clarity. JWST can analyze the light filtering through exoplanet atmospheres with exquisite sensitivity. It uses its large, gold-coated mirror, almost 21 feet across, to gather the faint infrared signals from distant worlds, concentrating them with remarkable efficiency. Imagine a giant silent eye, patiently collecting the invisible light, revealing hidden colors in a cosmic spectrum that our eyes cannot perceive. It is already providing us with the most detailed atmospheric spectra of exoplanets ever obtained, slowly unraveling the chemical compositions of worlds hundreds of light years away, one precise measurement at a time. While JWST is not specifically designed to find definitive biosignatures on Earth, like planets around sun-like stars, Its data will be invaluable in understanding the atmospheric chemistry of many diverse exoplanets, helping us to identify the most promising candidates for future, even more sensitive observations. It is the crucial first step, a gentle probing of the unknown in a long, patient investigation. Looking beyond JWST, scientists and engineers are already conceptualizing future observatories that will be specifically designed for the delicate task of finding biosignatures around Earth-like planets. These missions, often referred to as habitable world observatories, would be even larger and more complex than JWST. They might incorporate advanced technologies like starshades, var-shaped spacecraft designed to gently unfurl in space and block out the overwhelming glare of a parent star, allowing a direct, unhindered view of its orbiting planets. Imagine a cosmic eclipse, perfectly engineered to reveal the hidden worlds in exquisite detail, their faint light no longer drowned out by their brilliant sun. Such an instrument would allow astronomers to directly image an exoplanet and then perform spectroscopy on its light, rather than relying on the fleeting transit method. These future telescopes would be designed to patiently collect light from individual exoplanets for hundreds, even thousands, of hours, building up incredibly detailed atmospheric spectra, photon by photon. They would be capable of detecting much fainter biosignatures, and crucially, detecting them in combination, providing the necessary contextual clues to distinguish between biological and non-biological origins with high confidence. Such missions might involve multiple spacecraft working in concert, acting as a single immense cosmic instrument, gently gathering the ancient light from across the galaxy. The development and deployment of these observatories will be a long, patient journey spanning decades, involving immense technological leaps, but the potential reward, the quiet confirmation of life beyond Earth, is immeasurable, a profound moment for all of humanity. The immense patience and precision required for this endeavor is a profound testament to the human spirit of discovery and our unwavering intellectual curiosity. We are attempting to observe phenomena that are at the very limits of our technological capability, discerning patterns in light that has traveled for centuries or millennia to reach us. It is a task that demands deep calm, methodical perseverance, and an unwavering commitment to scientific rigor, ensuring that any claims of life are robust and thoroughly vetted. Each detection of an exoplanet, each faint spectral line identified, is a triumph of engineering and human curiosity, a step closer to understanding our place in the cosmic story. Imagine the quiet dedication of astronomers, gently guiding their colossal instruments to distant stars, meticulously analyzing streams of data, looking for the most subtle variations, the faintest whispers in the cosmic static. It is like listening to the deepest silence of the night, hoping for the gentle chime of a bell that might resonate from another world, carrying a message of life across the vast, tranquil darkness. This is not a search for dramatic, instantaneous answers, but a slow, patient unveiling, a gradual accumulation of knowledge, photon by photon, spectrum by spectrum. As we gently bring this segment to a close, let us reflect on this extraordinary journey. From the fundamental physics that allows light to carry chemical information across vast cosmic distances, to the ingenious methods we employ to capture and interpret that light, we are slowly, patiently learning to read the language of distant atmospheres. The quiet promise of biosignatures in the gentle filter of alien light reminds us that the universe is not just a collection of rocks and gas, but a canvas upon which the story of life may be written in countless diverse ways, each one a unique expression of cosmic possibility. We continue our patient vigil, ever hopeful, ever listening for the silent breath of other worlds, a profound discovery waiting to be made in the gentle glow of ancient starlight. As we float further into this vast topic, the patient vigil, listening for intelligent voices, our journey through the cosmos now shifts its focus, moving from the subtle, unconscious breath of life to the captivating possibility of deliberate communication. Imagine for a moment that our silent search for biosignatures, those chemical whispers in distant atmospheres, eventually yields a positive result. This would be a revelation of profound significance, confirming that life is not unique to Earth. Yet, the search extends further, reaching for an even more transformative discovery, the quiet echo of intelligence across the vast, tranquil expanse. This segment of our exploration delves into the organized, persistent efforts to listen for deliberate signals, using the immense emptiness of space as our canvas, and the universe's quiet hum as our background. We embark on a cosmic vigil, a patient listening for intelligent voices, a search not for rocks or gases, but for meaning. The foundational premise of the search for extraterrestrial intelligence, or SETI, is elegantly simple yet deeply profound. It rests on the hypothesis that if intelligent, technologically capable life exists elsewhere in the universe, it might, at some point, choose to communicate its presence. This isn't a search for biological organisms themselves, but for the products of their technology, specifically signals that carry information, signals designed to convey purpose and intellect. Think of it as tuning a cosmic radio, not for atmospheric static, the random hiss of the universe, but for a deliberate, modulated melody, a pattern that clearly speaks of intelligence, a deliberate message sent with intention. The underlying assumption is that any advanced civilization would eventually reach a stage where it could, and perhaps would, harness electromagnetic radiation, like radio waves or light, to broadcast its existence. This could be done either intentionally, as a beacon to others, or through incidental leakage from its own burgeoning technological activities, much like our own planetary broadcasts quietly escape Earth. This premise invites us to contemplate the quiet journey of civilizations. Just as humanity has sent probes into space and broadcast radio signals for over a century, a more advanced civilization might have been doing so for far longer, perhaps for millions of years. Our own planet has been quietly broadcasting its presence into space for decades, through early television, radio, and radar transmissions. These signals, though unintentional and growing fainter with distance, drift outwards, expanding silently into the galaxy at the speed of light, an ever-growing bubble of human technological presence. Perhaps other civilizations do the same, inadvertently creating a subtle, expanding sphere of their presence, an accidental footprint on the cosmic landscape. The SETI effort is precisely an attempt to detect such signals, to listen for any sign of a technologically distinct presence amidst the natural cosmic background, a quiet anomaly in the vastness. It is a quiet act of cosmic humility and profound hope, recognizing that our own story might be just one chapter in a much larger, untold narrative. However, this quest immediately confronts an immense challenge, often referred to as the cosmic haystack problem. Imagine searching for a single tiny needle, not just in a haystack, but in a haystack as large as a continent or even an entire planet, one that is constantly growing and shifting. The universe is unimaginably vast, with hundreds of billions of stars in our galaxy alone and countless galaxies beyond. Each star might host multiple planets, each planet a myriad of potential frequencies and directions from which a signal might emanate. To search effectively, we must consider an enormous range of possibilities, which stars to observe, for how long, at what precise frequencies, and with what kind of modulation or encoding. It's like trying to find one specific channel on a radio that has an infinite number of stations, while also needing to know precisely where the transmitter is located in a boundless, ever-changing landscape. This challenge underscores the deep patience and systematic approach required for the SETI endeavor, a long-term commitment of resources and intellect. The search space for SETI can be broken down into several dimensions, each requiring careful consideration and meticulous exploration. First, there's the spatial dimension, which stars, which regions of the sky should we point our sensitive instruments towards? Should we focus on stars similar to our sun, hypothesizing that life might arise in similar conditions, or should we consider the far more numerous and incredibly long-lived red dwarfs, which could offer billions of years more time for life to evolve? Do we survey entire star fields, or carefully target individual promising systems? Then there's the frequency dimension. If a signal is being sent, what particular frequency would an alien civilization choose to transmit on? Radio waves span an enormous spectrum, from very low frequencies that travel through planetary atmospheres to extremely high ones that carry vast amounts of data. And finally, there's the temporal dimension. How long should we listen to any given target? A signal might be continuous, like a steady beacon, or it might be a brief repeating pulse, a periodic whisper in the dark, or even a one-time transmission of profound information. These vast, interconnected parameters create the daunting cosmic haystack, a testament to the quiet magnitude of the task and the immense challenge of finding a single, deliberate utterance. Given this colossal challenge, early SETI efforts had to make some judicious assumptions to narrow the search, to find a logical starting point in the vastness. The focus naturally gravitated towards using radio waves, for several compelling reasons that seemed universally applicable. Radio waves travel at the speed of light, making them the fastest known way to send information across interstellar distances. Crucially, they are not significantly absorbed by interstellar gas and dust, allowing them to propagate across light years with minimal interference. From a practical standpoint, they are relatively inexpensive to generate and detect over vast distances using large radio telescopes. They represent a universal means of communication, readily available to any technological civilization. Furthermore, Earth's own technological development showed that radio communication was an early and powerful tool for sending and receiving information, an early benchmark of technological prowess. So, it was a logical and pragmatic place to begin listening, a kind of cosmic common ground. Within the vast radio spectrum, scientists quickly identified a particular band of frequencies that seemed especially promising, a kind of waterhole in the cosmic static. Imagine a quiet, universally recognized meeting place for weary travelers across a vast, empty desert, a natural oasis where all might intuitively gather. This waterhole lies specifically between the frequencies emitted by neutral hydrogen at 1020 MHz, or 21 centimeter wavelength, and hydroxyl molecules at around 662 MHz. These two molecules, hydrogen and hydroxyl, are the chemical dissociation products of water. H2O, the very solvent for life as we know it, the essence of our existence. So, a civilization might intuitively choose this quiet, natural channel for communication, a frequency free from much of the universe's natural radio noise, as a universally understood beacon, a subtle nod to the shared importance of water. It's a serene, almost poetic, notion that alien intelligences might gravitate towards this cosmic waterholes to make contact, a testament to shared fundamental principles. The history of radio SETT is one of profound, quiet perseverance, a steady, unwavering commitment over generations. Beginning in 1960 with Project Ozma, a small team led by pioneering astronomer Frank Drake used a modest 85-foot radio telescope to listen to two nearby stars, Tau Ceti and Epsilon Eridani, for only a few months. That small, focused effort, though detecting no signals, laid the groundwork. Since then, numerous projects have followed, growing exponentially in sophistication and scope. Large radio dishes, like the iconic Arecibo Observatory in Puerto Rico before its unfortunate collapse, and the majestic Green Bank Telescope in West Virginia, have gently swept the skies, patiently gathering faint radio waves from countless stars. Imagine these immense dishes, like attentive, silent ears, patiently pointing upwards, slowly rotating, meticulously listening to the universe's faint murmur, filtering out the background noise. They collect data for months, even years, accumulating vast amounts of information, all of it carefully analyzed by powerful computers searching for any non-random pattern, any repetitive pulse, any signal that stands out unequivocally from the natural background hum of the cosmos. Modern SETI instruments can observe millions of frequencies simultaneously, vastly increasing their efficiency. These silent listening campaigns have been conducted over decades, often with limited funding, sustained by the quiet dedication of scientists and the enduring hope of humanity, a hope that transcends immediate results. While no definitive alien signal has yet been confirmed, no unmistakable message received, the absence of a detection does not, in any way, mean the absence of life. It simply means we haven't found it yet, or perhaps we haven't listened long enough, or in quite the right way, or at quite the right frequency. The universe is an ancient, unimaginably vast place, and our search, though decades long, has barely scratched its surface, exploring only a tiny fraction of the cosmic haystack. It's akin to dipping a single teacup into the Earth's immense oceans, and then, finding no fish, declaring the oceans empty of all marine life. The sheer scale of the universe demands continued, patient vigilance and an unwavering scientific commitment. As our understanding of technology has evolved, so too has our approach to SETI, adapting to new possibilities. While radio remains a cornerstone, a new field has emerged: optical SET. This method shifts our focus from the broad spectrum of radio waves to the narrower, yet equally promising spectrum of light, specifically looking for brief, powerful flashes of light that might originate from advanced laser communication systems. Imagine, instead of a steady radio beacon, a civilization choosing to send incredibly short, intense pulses of laser light aimed directly at us or sweeping across vast areas of space in a targeted fashion. Why lasers? Lasers offer several compelling advantages for interstellar communication, particularly for highly advanced civilizations. They can be focused into incredibly tight, coherent beams, allowing a civilization to direct a powerful signal with much less energy than would be required for an omnidirectional radio broadcast, which spreads its energy across all directions. A focused laser pulse, even for a mere nanosecond, could briefly outshine its parent star in its specific direction, making it potentially detectable across vast distances, even if it's only for a fraction of a second. Picture a distant lighthouse, its powerful beam briefly cutting through the deepest fog, appearing brighter than anything else for that fleeting moment, a sharp, distinct flash. The brevity and intensity of such a pulse would instantly mark it as artificial, standing out against the steady, natural glow of stars. The search for optical SETI signals involves custom-built telescopes equipped with extremely fast light detectors, capable of measuring light fluctuations in picoseconds. These instruments patiently observe target stars, looking for rapid, non-natural flashes of light that last only nanoseconds or microseconds. It's a different kind of listening, a silent vigil for subtle flickers in the cosmic tapestry, a quest for brief, intense pulses that stand out sharply from the steady, unchanging glow of natural starlight. These programs are often run in parallel with traditional radio SETI, exploring another plausible avenue for interstellar communication, expanding our cosmic ears to another part of the electromagnetic spectrum, hoping for a quiet, unexpected flash, a sudden, deliberate spark in the darkness. The inherent challenges of interstellar communication are immense, underscoring the profound patience required for this endeavor. The most obvious challenge is the vast distances involved. Even the closest star systems are light years away, meaning any signal we send or receive takes years to traverse the cosmic void. For example, a signal traveling at the speed of light to the nearest known star system, Proxima Centauri, would take over 4 years to arrive. A reply would take another 4 years to return. This creates millennia-long time, delays for any meaningful, back-and-forth conversation across truly vast interstellar distances. Imagine trying to have a conversation with a friend across an ocean, and it takes centuries for your message to arrive, and centuries more for their reply to reach you. This vast temporal separation means that interstellar communication, if it ever occurs, would not be a rapid exchange, a quick chat, but rather a slow, meditative dialogue unfolding over geological timescales across generations. A civilization sending a message might be long gone by the time we receive it, having risen and fallen, and we might be long gone by the time our reply reaches them. This underscores the profound, quiet patience required, a patience that transcends individual lifetimes and demands a generational commitment, a long-term vision passed down through history. It also suggests that any signals we might detect are likely to be designed for maximum longevity and clarity, perhaps simple mathematical sequences, prime numbers, or fundamental physical constants, or even pictorial representations, like the elegant patterns on the Voyager golden records, intended to be understood by any intelligence, regardless of language or fleeting cultural context. These messages would be designed to stand the test of cosmic time. The challenges extend beyond mere distance and time. There's the crucial issue of signal strength and noise. Even a powerful broadcast, designed for interstellar distances, diminishes significantly over light years, spreading its energy thinly across space. By the time a signal reaches us, it would be incredibly faint, barely distinguishable from the natural background noise of the universe itself, the cosmic microwave background, the radio emissions from distant galaxies, the crackle of our own star. Imagine trying to hear a whispered secret from across a vast echoing canyon, filled with the roar of a waterfall. Our instruments need to be incredibly sensitive, carefully filtering out not only terrestrial interference from our own technologies, but also cosmic static to discern any true artificial patterns. This requires sophisticated signal processing techniques, constantly refined by dedicated engineers and scientists. If we receive a signal, how would we decode it? Would it be in a universal language of mathematics, which is often hypothesized as the most likely shared language, or something far more esoteric and culturally specific? The very act of deciphering such a message, if it were complex, could take decades or even centuries of dedicated intellectual effort, a profound, quiet intellectual puzzle spanning generations of researchers. These challenges are not insurmountable, but they demand a deep humility, a recognition of our place in the vastness of cosmic time and space, and an openness to entirely new ways of thinking. The calm, persistent nature of this search is truly remarkable, embodying a unique blend of scientific rigor and philosophical introspection. It is akin to patiently tuning a cosmic radio dial for a faint, distant melody, slowly and meticulously sweeping across countless frequencies, hoping to catch a pure, modulated tone amidst the vast static. It is a scientific endeavor, driven not by immediate gratification or the promise of quick results, but by a deep, unwavering philosophical curiosity and the profound human desire to know if we are alone. Researchers dedicate their entire careers to this work, knowing that a discovery, if it comes, might not happen in their lifetime, but perhaps in the lifetimes of their grandchildren or great-grandchildren. This intergenerational dedication embodies the true spirit of long-term scientific pursuit, a quiet, sustained hope that resonates across time, a testament to humanity's capacity for boundless patience. Imagine the immense radio dishes, like the thousands of individual antennae that comprise the Allen Telescope Array in California, gently sweeping the night sky, their collective gaze directed outwards. They are patiently listening, not in a hurried, frantic search, but with a meditative, focused attention, collecting a ceaseless torrent of data. The data streams flow endlessly into supercomputers, which quietly process trillions of data points every second, searching for patterns that defy natural explanation, for the unmistakable signature of intelligence. This is not a frantic sprint for a quick answer, but a steady, deliberate marathon, a quiet act of listening to the universe itself, waiting for a response to our unspoken questions. The profound silence that has greeted us thus far is not a sign of failure, but rather a reflection of the immense scale of the search and the quiet patience required to overcome it, to truly give the universe time to respond. It's important to make a gentle distinction between two approaches in this cosmic conversation: passive listening, which is the essence of SETI, and active messaging, known as METI. The search for extraterrestrial intelligence, or SETI, as we have been discussing, is a purely passive endeavor. It involves listening to the universe, hoping to detect signals that other civilizations might be sending, either intentionally as a deliberate beacon or as a byproduct of their own technological activities, a kind of incidental cosmic leakage. It's like gently observing from a distance, without revealing your own presence, patiently waiting for a sign. This approach is widely supported within the scientific community, as it poses no immediate risk and offers immense potential reward: the profound knowledge that we are not alone. METI, or Messaging Extraterrestrial Intelligence, takes a different, more active stance. This involves intentionally sending powerful, deliberate messages into space, designed to announce humanity's presence and potentially communicate information about our civilization, our science, our art, and our existence. The most famous example of this was the Arecibo message, a pictorial radio message encoded in binary and sent in 1974 towards the M13 globular cluster, a collection of hundreds of thousands of stars, about 25,000 light-years away. Other, less powerful, signals have also been sent, such as the Voyager Golden Records, phonograph records containing sounds and images of Earth, placed aboard the Voyager spacecraft, which are now slowly drifting out of our solar system, carrying a silent message across the interstellar void. The concept of METI sparks a quiet, yet profound, debate among scientists and philosophers, a deep reflection on our cosmic responsibilities. On one hand, proponents argue that if we truly wish to make contact, we must actively participate in the cosmic conversation rather than just passively listening, waiting for others to find us, might take far too long or never happen at all. They believe that intelligently designed messages, carefully crafted to convey universal truths, could be our best chance to bridge the vast distances and initiate a dialogue. On the other hand, critics voice a note of caution, suggesting that we do not fully understand the potential implications of broadcasting our presence. We have no way of knowing the nature or intentions of any civilization that might receive our message. Would they be benevolent, indifferent, or potentially hostile? This quiet debate is a deep reflection on our cosmic responsibilities, a thoughtful contemplation of our role as a nascent technological species in a vast unknown universe, urging us to proceed with wisdom and foresight. For now, most efforts remain focused on the passive, patient listening of SETI, maintaining a respectful silence while we learn more about the cosmic neighborhood, gently gathering information before broadcasting our own definitive statement. As we gently bring this segment to a close, let us reflect on the profound patience inherent in the search for intelligent voices. It is a testament to humanity's enduring curiosity, our deep-seated desire to understand if we are alone in this magnificent cosmic tapestry, or if there are other minds out there pondering the same quiet questions. Whether through sweeping radio dishes listening for faint hums, or optical telescopes seeking brief flashes, the quest is a long, deliberate act of observation and analysis, a quiet vigil spanning generations. The profound silence we have encountered thus far is not a sign of futility, but rather an invitation to deepen our resolve, to continue our patient search. Perhaps one day, amidst the gentle static of the universe, a faint rhythmic pulse will emerge, a melody from across the stars, signaling that we are not alone. And in that quiet moment, the long, patient wait will have found its profound, peaceful resolution, forever changing our understanding of life in the cosmos. As we drift deeper into our exploration, direct exploration, probing the solar system's secrets, our gentle journey through the cosmic quest for life now brings us closer to home, within the quiet confines of our own solar system. Having patiently listened for the whispers of alien atmospheres and the potential echoes of distant intelligence, we now embark on a more intimate exploration. This segment delves into the dedicated robotic missions, our silent emissaries, that actively seek direct evidence of past or present life on other worlds. From the rust-colored plains of Mars to the frozen husks of icy moons, we will uncover how these diligent machines meticulously probe these worlds, searching for telltale signs, gently uncovering their secrets, one quiet experiment at a time. This direct, hands-on approach allows us to gather tangible evidence, patiently and systematically. For centuries, Mars, our near neighbor, has captivated human imagination, often pictured as a world that might harbor life. Its reddish hue, reminiscent of desert landscapes on Earth, and the fleeting appearance of what were once thought to be canals, fueled dreams of Martian civilizations and verdant landscapes. These early, imaginative notions were born from telescopic observations that, while inspiring, could not reveal the planet's true nature. Our scientific exploration of the red planet began more cautiously, evolving into a long and patient history of searching for life, a methodical, step-by-step investigation that has stretched over decades and involved dozens of spacecraft. It is a testament to sustained curiosity and technological advancement. The first truly dedicated missions to directly search for life on Mars were the pioneering Viking landers in 1976. These two spacecraft, Viking 1 and Viking 2, gently touched down on the Martian surface at two distinct locations, Chrysa Planitia and Utopia Planitia, carrying highly sophisticated biology experiments designed to detect microbial life. These experiments cautiously sought signs of metabolism. For instance, one experiment looked for changes in gases released from Martian soil after it was incubated with nutrients. Another looked for uptake of radioactive carbon by potential microbes. Imagine tiny robotic arms, carefully extending from the lander's body, delicately scooping up reddish soil and delivering it to miniature, enclosed laboratories within the lander, all in the silent, thin Martian atmosphere. The results from the Viking experiments were, at the time, ambiguous and widely debated. One experiment, the labeled release experiment, did show a transient positive result, indicating some activity, but this was generally attributed to unusual, highly reactive chemistry in the Martian soil, perhaps involving peroxides rather than definitive biological processes. Crucially, Other instruments on Viking found no definitive organic molecules, the building blocks of life, in the soil, casting doubt on the biological interpretation. The Viking missions taught us a crucial lesson. The search for alien life is incredibly complex and requires careful, conservative interpretation, distinguishing between truly biological activity and fascinating but abiotic chemistry. Their legacy, however, remains foundational, establishing the rigorous scientific methodology that continues to guide our current missions. They were our first quiet footsteps onto another world in search of life. Following Viking, our approach to Mars evolved, shifting from a direct life detection strategy to a more focused, follow-the-water strategy. We realized that understanding the planet's past habitability, whether it ever could have supported life, was the logical and necessary precursor to finding life itself. This subtle shift in strategy led to a continuous series of orbiters, landers, and rovers, each building upon the knowledge of its predecessors, patiently unraveling the Martian story, piece by quiet piece. This journey began with orbiters providing the grand overview, then landers offering stationary insights, and finally rovers enabling mobility and detailed ground-level exploration. And the story revealed by these quiet robotic explorers was truly compelling, transforming our understanding of Mars. Orbiters like Mars Global Surveyor and Mars Odyssey, and later the incredibly capable Mars Reconnaissance Orbiter, provided breathtaking high-resolution images of the Martian surface, revealing intricate geological features that spoke volumes about its past. These images presented compelling evidence of abundant ancient water on Mars, vast river valleys, some hundreds of miles long and several miles wide, gently winding across the landscape, starkly reminiscent of ancient river systems on Earth. We saw dried-up lake beds, sometimes with delicate, layered structures of sedimentary rock, indicating tranquil lakes that once existed for extended periods, perhaps millions of years. Imagine ancient shorelines, now just subtle topographical changes, etched into the red dust, marking where calm waters once gently lapped against the land. We even found compelling evidence, through studies of topography and mineral distribution, suggesting that Mars might have hosted early oceans, particularly in its northern lowlands, billions of years ago. These oceans, though long gone, paint a picture of an early Mars that was far warmer, wetter, and potentially more hospitable to life than it is today, a blue Mars instead of a red one. This understanding fundamentally changed our perspective, transforming Mars from a dead, arid world into one with a rich, dynamic, watery past. Our robotic rovers have provided even more intimate details, like patient geologists slowly traversing the terrain. Spirit and Opportunity, two intrepid rovers, patiently explored for years beyond their expected lifespans, finding clear evidence of past surface water, including minerals that only form in the presence of liquid water, like sulfates and hematite blueberries, small spherical concretions of iron oxide that typically form in water-rich environments. Curiosity, landing in Gale Crater in 2012, meticulously explored an ancient lake bed for over a decade, finding compelling evidence of a freshwater lake that existed for millions of years. It drilled into mudstone rocks, discovering the essential chemical ingredients necessary for life as we know it: carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur, all quietly embedded within the ancient lake sediments. It also detected various organic molecules, the very building blocks of life, gently preserved within the rock, confirming the presence of complex carbon chemistry. This groundbreaking discovery confirmed that Gale Crater, billions of years ago, possessed not only liquid water, but also the chemical energy and environmental conditions suitable for microbial life, a truly habitable environment. The most advanced rover currently exploring Mars is Perseverance, which made a gentle, precise landing in Jezero Crater in 2021. Jezero Crater is a particularly tantalizing target because it features a beautifully preserved ancient river delta, a fan-shaped geological structure formed where a river once flowed into a lake. Deltas on Earth are incredibly rich environments for life, as they deposit fine-grained sediments that can effectively trap and preserve organic molecules and fossilized microbial signs for eons. Perseverance's mission is explicitly focused on the ongoing search for definitive, fossilized microbial life from this ancient, watery past. It is meticulously examining rocks that are prime candidates for preserving biosignatures, carefully selecting samples that represent the most promising locations for past life. Imagine the quiet whir of its robotic wheels, slowly traversing the ancient lakebed, its advanced instruments patiently analyzing every stone and patch of dust, each one a potential page in Mars's biological history. The Mars-Cam Z cameras provide stunning stereo images, while the SuperCam uses a laser to vaporize tiny bits of rock and analyze their composition. Beyond fossilized remnants from a distant past, the search for life on Mars also includes the quest for present-day subsurface liquid water reservoirs. While the surface of Mars is too cold and the atmosphere too thin for stable liquid water today, there is strong evidence that briny, salty water could exist beneath the surface, warmed by internal heat, or perhaps held in suspended pockets within the ice. Orbiters have detected intriguing dark streaks on Martian slopes, called recurring slope lineae, that appear seasonally, suggesting flows of salty water, too briny to freeze in the Martian cold. Ground-penetrating radar on orbiters has also found evidence of a large, stable body of liquid water beneath the South Polar ice cap. Future missions might involve gentle drills designed to penetrate deeper into the Martian crust, searching for these hidden reservoirs, places where existing microbes might find refuge from the harsh surface environment, shielded from radiation and extreme temperatures. This patient, methodical approach is slowly piecing together the true story of Mars, one geological layer, one chemical signature at a time, guided by the profound question of life. The success of all these missions relies on the sophisticated techniques of robotic exploration, a testament to human ingenuity and the quiet dedication of thousands of engineers and scientists over many decades. These spacecraft are far more than simple remote-controlled vehicles. They are highly autonomous, self-sufficient laboratories, capable of making complex decisions and adapting to their environment, albeit with a gentle, programmed precision, executing intricate sequences of commands from Earth. Their ability to operate for years, beyond their design life, is a marvel of engineering. Imagine a rover like Perseverance in action. Its numerous high-definition cameras provide a panoramic, detailed view of its surroundings, allowing it to navigate the treacherous Martian terrain with a quiet grace, avoiding hazards autonomously. It carries a suite of advanced scientific instruments, each a miniature marvel, spectrometers to analyze the chemical composition of rocks and soils from a distance, and up close, a ground-penetrating radar to see beneath the surface, and a sophisticated drill that can gently penetrate into solid rock, extracting pristine core samples. These cores, about the size of a piece of chalk, are then meticulously sealed in sterile titanium tubes, precisely catalogued, and deposited in designated spots on the Martian surface, forming the foundation of the ambitious Mars Sample Return mission. The Mars Sample Return mission is perhaps the pinnacle of robotic exploration planning, representing a multi-decade international effort. It is a multi-stage effort to bring Martian rock and soil samples back to Earth for unparalleled scientific analysis. Imagine the ultimate scientific treasure hunt, unfolding across planets and through space. Perseverance collects its samples over several years, then deposits them in a designated spot on the Martian surface. A future lander, the Sample Retrieval Lander, would then arrive, carrying a small rover to collect these sealed sample tubes. Once collected, these tubes would be loaded into a small rocket, the Mars Ascent Vehicle, which would launch them into Mars orbit. Finally, an Earth return orbiter would rendezvous with the sample container in Martian orbit, capture it, and gently return it to Earth for a safe landing. This incredibly complex ballet of autonomous spacecraft, unfolding over the next decade, represents the ultimate form of direct exploration without human presence. Bringing samples back to Earth would allow scientists to use our most powerful laboratories, free from the constraints of a remote mission and with instruments too large or complex to send to Mars, to search for the most subtle biosignatures, to truly discern the presence of past or present life with unmatched precision and certainty. It is a slow, patient, and methodical process, but one with the potential for epoch-making discoveries that could fundamentally alter our understanding of life in the universe. Beyond Mars, our gaze extends to the ocean worlds we briefly touched upon in our previous discussion. These icy moons, with their hidden liquid water environments, are now prime targets for direct exploration, requiring different, yet equally ingenious, robotic approaches. Our understanding of Europa and Enceladus has grown immensely through flybys and remote sensing, revealing their watery secrets, but to truly search for life, we need to get closer, to penetrate their icy veils, to gently sample their hidden depths. Looking ahead, the Europa Clipper mission is currently under development and scheduled for launch in the coming years. Its design is for multiple close flybys of Europa, rather than a single orbital insertion, which helps to minimize radiation exposure from Jupiter's harsh radiation belts, allowing the spacecraft to operate for longer. It will carry a suite of 9 sophisticated instruments, including powerful radar that can gently penetrate Europa's icy shell, mapping the subsurface ocean's depth, salinity, and potential zones of warmer water. It will also look for any faint plumes erupting from the Moon's surface, similar to those seen on Enceladus, to potentially sample them directly, like a quiet hand reaching out to touch a secret. Imagine a spacecraft patiently orbiting Jupiter, making precise, close passes over Europa, like a gentle hummingbird delicately sampling nectar, gathering every possible piece of information about the hidden ocean. The data it collects will be crucial in planning future missions that might one day land on Europa's surface and perhaps even deploy a submersible, a deep-sea vehicle for space, into its dark, deep ocean, a truly astonishing prospect. Even further into the future, the Dragonfly mission to Titan represents an entirely new paradigm in planetary exploration. Instead of a rover traversing a surface or an orbiter circling above, Dragonfly is a robust, nuclear-powered rotorcraft, essentially a robotic drone with 8 rotors. It is designed to fly through Titan's thick, nitrogen-rich atmosphere, quietly and gracefully hopping between dozens of scientifically compelling locations across the Moon's diverse landscape, covering distances far greater than any wheeled rover. Imagine a giant silent dragonfly, gently descending into Titan's hazy orange sky, then soaring effortlessly over its hydrocarbon lakes and extensive dune fields, settling down softly to conduct experiments in different chemical environments. It will carry a full suite of instruments to analyze the composition of Titan's surface materials, its atmosphere, and, crucially, to search for complex organic molecules and potential chemical biosignatures in its frigid liquid methane environments. This mission represents a bold, innovative leap, designed to explore an utterly alien world with an unprecedented level of mobility and intimacy, a patient and agile scout for exotic life, constantly adapting to its unique environment. Our solar system, however, holds other intriguing bodies that whisper possibilities of life, expanding our patient search beyond the most prominent targets. Consider Ceres, the largest object in the asteroid belt, nestled quietly between Mars and Jupiter. Once thought to be a simple rocky asteroid, Ceres has revealed itself, through the meticulous observations of the Dawn mission, to be a more complex, geologically active dwarf planet. Its most mysterious features are the incredibly bright spots within its craters, now understood to be large deposits of salt, likely left behind by upwellings of briny water from beneath the surface, which then evaporated. This strongly suggests that Ceres may harbor a subsurface ocean of liquid brine, warmed by leftover heat from its formation and the decay of radioactive elements, a quiet, hidden sea in the asteroid belt. Imagine this quiet dwarf planet, slowly releasing its ancient salty tears, a subtle hint of a hidden liquid reservoir, a tiny, unexpected world holding a secret liquid heart. Then there is Venus, our planetary neighbor, often dismissed as entirely inhospitable due to its crushing atmospheric pressure, dense sulfuric acid clouds, and searing surface temperatures, hot enough to melt lead. Yet, in 2020, a tantalizing hint emerged, the detection of phosphine gas in Venus's upper atmosphere, specifically in the more temperate cloud layers about 30 to 40 miles above the surface. Phosphine is a gas that, on Earth, is almost exclusively produced by microbial life in anaerobic environments, places devoid of oxygen. While the detection itself was later debated, and the conditions in Venus's upper atmosphere are still incredibly challenging, this discovery sparked a quiet scientific re-evaluation, forcing us to consider even the most extreme environments. Could there be aerial microbial life, perhaps floating peacefully within the more temperate cloud layers of Venus, shielded by sulfuric acid droplets, surviving on entirely different chemical pathways, patiently adapting to an incredibly harsh niche? This intriguing possibility reminds us that life might find niches in the most extreme, unexpected places, challenging our preconceptions and urging us to keep all doors open in our patient, cosmic search. As we gently conclude this segment of our exploration, we reflect on the meticulous, patient work of robotic hands and minds, our silent emissaries, from the methodical rovers patiently traversing the plains of Mars, to the visionary rotorcraft for Titan and the orbiters mapping distant icy worlds, are gradually, gently uncovering the profound secrets of our solar system. Each drilled core, each sampled plume, each atmospheric analysis brings us closer to understanding the conditions that foster life, and perhaps, one day, to finding direct evidence of its existence. It is a testament to humanity's enduring curiosity, patiently guided by the gentle rhythm of scientific discovery, that we continue to probe these worlds, ever hopeful, ever learning, quietly awaiting the next revelation from across the cosmic expanse, a revelation that could change everything we know about life's quiet journey. Our journey through space now brings us to the great silence and the unfolding future of discovery. Our gentle journey through the cosmic quest for life has taken us across immense distances and through deep time, from the stellar nurseries where elements are born, to the hidden oceans of icy moons, and the subtle atmospheric whispers of distant worlds. We have patiently considered the possibility of intelligent signals. Yet, as we approach the quiet close of our exploration, we calmly confront a grand, unanswered question, one that has gently puzzled thinkers for decades, the profound silence we have encountered thus far. This is the essence of the Fermi paradox, a thought experiment that asks, quite simply, where is everybody? Imagine the vastness of our Milky Way galaxy, a serene spiral of hundreds of billions of stars, many of which are older than our Sun, and many of which likely host planets within their habitable zones. The calculations from the Drake equation, though highly speculative, consistently suggest a potentially large number of technological civilizations could exist within our galaxy alone. If life emerges easily, as suggested by Earth's relatively rapid development of early life, and if intelligence is a natural evolutionary outcome, perhaps driven by environmental pressures, then statistically our galaxy should be teeming with civilizations. Some of these civilizations, having formed around older stars, should be far more ancient than our own, having had billions of years to develop advanced technologies, to spread across their star systems, or even to begin interstellar travel and colonization. If even a small fraction of these civilizations were to expand and colonize, they could theoretically populate the entire galaxy in just a few million years, a mere blink in cosmic time, given the immense timescales available. So, if they are out there, if the galaxy should be teeming with them, why haven't we seen any clear, unambiguous signs? Why the profound, pervasive silence? This apparent contradiction between the high probability of alien life and intelligence, supported by the sheer number of exoplanets we now detect, and our persistent lack of direct evidence, is the quiet heart of the Fermi paradox. It is not an alarming mystery designed to provoke anxiety, but rather a peaceful puzzle, an invitation to deep contemplation, inviting us to explore the various reasons that might explain this cosmic silence. There are no definitive answers, only a spectrum of fascinating possibilities, each offering a gentle reflection on our place in the universe and the potential pathways of life elsewhere. The paradox quietly challenges our assumptions about life, intelligence, and the universe itself. One intriguing category of explanations for the Fermi paradox revolves around the concept of great filters. Imagine that along the long, complex path from the emergence of simple life to the development of a widespread, intelligent, and interstellar capable civilization, there exists one or more immense cosmic challenges, a kind of evolutionary filters that most life, or most intelligent life, simply cannot overcome. These filters could be located in our past, meaning we are a rare exception that successfully navigated them, or they could lie ominously in our future, hurdles we have yet to face. They are cosmic hurdles, quietly and effectively preventing the proliferation of advanced, spacefaring life throughout the galaxy. Let's gently explore some of these proposed great filters. One possibility suggests that the filter lies deeply in our past, making the emergence of complex, intelligent life incredibly rare. Perhaps the very genesis of life from non-living matter, the step of abiogenesis, is far more difficult and improbable than we currently appreciate. Imagine the intricate, delicate dance of molecules that must occur, the precise environmental conditions, the immense stretches of time required for the first self-replicating systems to arise in a primordial soup. If this step is exceedingly improbable, then Earth might be a profound anomaly, a rare flower in a vast, barren cosmic garden, having passed this incredibly stringent filter. Or perhaps the transition from simple, single-celled life to complex, multicellular organisms requiring the development of intricate cellular cooperation represents another immensely difficult hurdle that very few evolutionary pathways ever manage to cross. The evolution of true intelligence, leading to tool use and complex communication, might be yet another such filter, a cognitive leap that is rare indeed. These are quiet possibilities, suggesting that we are rare because the universe itself has immense, subtle, yet powerful barriers to overcome early in the story of life. Alternatively, the great filters could lie in our future. This is a more sobering, yet still calmly contemplated, possibility. One that asks us to reflect on our own trajectory. Perhaps intelligent civilizations tend to destroy themselves before they achieve interstellar travel or widespread galactic colonization. This self-destruction could come in various forms, through technological mishaps, such as the accidental creation of rogue AI or bioweapons, through resource depletion, where a civilization exhausts its planetary resources before it can sustainably expand, or through unchecked aggression leading to global warfare. Imagine a civilization reaching a peak of technological prowess, capable of immense feats, and then quietly, almost inevitably, succumbing to its own advancements or internal conflicts. Or perhaps there is a naturally occurring cosmic catastrophe that frequently wipes out advanced life, like a periodic, powerful burst of gamma rays from a distant star, silently sterilizing entire regions of a galaxy with a wave of lethal radiation, or perhaps a close encounter with a rogue black hole or star. These ideas suggest that the quiet we hear is not because life is rare to emerge, but because intelligent life simply doesn't last very long once it reaches a certain level of technological capability. This contemplation encourages us to reflect on the fragility of our own civilization and the paramount importance of sustainability, cooperation, and wisdom in navigating our own future. Closely related to the Great Filter concept are two broad hypotheses that frame our understanding of life's prevalence, the rare Earth hypothesis versus the abundant life hypothesis. Let's consider these as gentle thought experiments, allowing us to quietly weigh the scientific possibilities and their implications. The rare Earth hypothesis, first articulated by Peter Ward and Donald Brownlee, suggests that the combination of astronomical and geological conditions that allowed for complex, intelligent life to emerge and thrive on Earth is exceptionally rare, perhaps even unique within our galaxy or beyond. It argues that for complex life, not just microbial life, to flourish and evolve, a precise confluence of many factors is needed, a long list of cosmic prerequisites. This includes having a star of just the right size and type, like our Sun, which provides stable energy output over billions of years, but not too much harmful radiation. This star must orbit in a stable galactic region, far enough from the chaotic, radiation-filled galactic center, but close enough to gather the heavy elements needed for planet formation. It requires a planet with a stable, near-circular orbit, maintaining consistent temperatures, and critically, a large moon to stabilize its axial tilt, ensuring stable seasons and preventing extreme climate swings. Furthermore, the presence of plate tectonics is thought to be essential for recycling nutrients, regulating the climate through the carbon cycle, and creating diverse habitats. It also needs a giant outer planet like Jupiter to act as a cosmic vacuum cleaner, gently deflecting disruptive comets and asteroids, protecting the inner planets from frequent, sterilizing impacts. Imagine a long, delicate chain of perfect circumstances, each link essential, and if any one link is missing or broken, the chain of complex life cannot form or will be quickly extinguished. This hypothesis, if true, would mean that Earth is indeed a precious, lonely jewel in the cosmic expanse, a profound rarity, and the silence we hear is simply because there's very little complex company out there. In contrast, the abundant life hypothesis posits that life, particularly microbial life, is probably widespread throughout the universe. It suggests that if the fundamental conditions for life are met, the presence of liquid water, a source of energy, and the right chemical building blocks, then life will likely emerge, a natural outcome of cosmic chemistry. This hypothesis is strongly bolstered by our discoveries of extremophiles on Earth, thriving in environments once thought utterly impossible for life. Sush on Earth, thriving in environments once thought utterly impossible, such as hydrothermal vents, acidic lakes, or even within solid rock deep underground. It is also supported by the numerous ocean worlds in our solar system, like Europa and Enceladus, that hold vast quantities of liquid water, an essential solvent. If life is abundant, then the Fermi paradox points more strongly towards a future great filter, or perhaps to issues of detectability, suggesting that civilizations might simply be too far apart, too short-lived, or perhaps communicate in ways we haven't yet learned to perceive, making their presence undetectable to our current methods. This perspective offers a more comforting vision, one where life is a common, quiet hum across the galaxy, a pervasive force, even if intelligence remains elusive or chooses to be silent. These two hypotheses offer different frameworks for our ongoing scientific puzzle, inviting peaceful contemplation rather than definitive judgment, encouraging us to remain open to all possibilities. As we gently shift our gaze from these profound philosophical considerations to the horizon of scientific possibility, we find ourselves contemplating the future technologies that will shape the hunt for life in the coming decades. Science is a continuous, patient unfolding, a relentless pursuit of knowledge, and our tools for discovery are constantly being refined, expanded, and reimagined, allowing us to delve deeper into the cosmic unknown. One of the most exciting areas of advancement lies in advanced space telescopes with unprecedented capabilities. We briefly discussed the James Webb Space Telescope, a powerful infrared eye that is already revealing wonders. Looking ahead, conceptual, habitable worlds observatories are being planned. These future observatories will be designed to directly image Earth-sized exoplanets orbiting sun-like stars, a feat that is currently beyond our reach, where the tiny planet is completely overwhelmed by its star's glare. Imagine a telescope so powerful, so exquisitely sensitive, that it could resolve a tiny pale blue dot orbiting a star light years away, a point of light among billions, and then, with even more advanced instruments, gently unfurl that faint light into a spectrum to analyze its atmosphere directly, looking for biosignatures. Such telescopes might incorporate advanced coronagraphs, which precisely block the star's light within the telescope, or deploy vast petal-shaped spacecraft known as starshades, designed to gently block out the overwhelming glare of the host star from many thousands of miles away, much like holding a thumb up to block a car's headlight to see the small objects around it. This would allow us to study exoplanet atmospheres with a clarity and precision never before possible, bringing the distant whispers of life into much clearer focus. Beyond our immediate solar system, imaginative new concepts for interstellar probes are being gently explored, pushing the boundaries of what is possible within conventional physics. While faster-than-light travel remains firmly in the realm of science fiction, we are investigating ways to travel much faster than our current spacecraft. Projects like Breakthrough Starshot are investigating the feasibility of sending tiny, wafer-thin spacecraft, perhaps just a few grams in mass, propelled by powerful ground-based lasers to nearby star systems. Imagine a fleet of these minuscule, silent probes, gently accelerated by focused light beams to a significant fraction of the speed of light, perhaps 20% the speed of light, carrying miniature scientific payloads. At such speeds, they would take decades, not millennia, to reach nearby stars, offering the breathtaking possibility of direct imaging and data collection from worlds light years away within a single human lifetime. This is a profound leap, transforming our passive listening into active, albeit slow, visitation, a true physical reach across the cosmic void. These concepts represent a profound shift, offering a long-term vision for physically reaching out to the stars, even if the journey is a long, patient drift through the interstellar void, collecting data and returning it to us. Our evolving understanding of life also broadens our definition of what to search for. The concept of biosignatures, those chemical whispers of biology, is expanding to include technosignatures, direct, observable evidence of technology rather than just biology. This goes beyond simply listening for radio signals. If advanced civilizations exist, they might leave other, more subtle, technological footprints in the cosmos, large-scale engineering projects or atmospheric modifications. Imagine, for instance, a distant exoplanet whose night side glows not just with the faint reflected starlight from its star or a nearby moon, but with the steady artificial illumination of cities, much like Earth appears at night from orbit, a delicate network of light. Or perhaps we could detect industrial pollution in their atmospheres, specific chemical compounds that are purely artificial. Even more ambitiously, we might search for evidence of immense stellar engineering projects, like Dyson spheres or swarms, vast structures built around stars to harness their immense energy. Such structures would subtly alter the star's light in ways that are unnatural, causing it to dim in unusual patterns or emit excess infrared heat. We might also search for unusual waste heat signatures from large-scale computing, or even the distinctive signals of interstellar probes or communication networks, far more complex than simple radio beacons. These techno-signatures are essentially the unintentional or intentional fingerprints of intelligence and technology, providing another, perhaps more direct, avenue for our patient search. It is a quiet quest for the subtle alterations that intelligence might impose on its environment, a search for the conscious rather than the purely natural, a sign of deliberate action rather than passive existence. As we contemplate the profound implications of discovery, we also turn our thoughts to the ethical considerations surrounding potential contact and the paramount importance of planetary protection in our own exploration efforts. If we were to definitively discover alien life, especially intelligent life, it would undoubtedly be the most significant scientific and philosophical event in human history, challenging our deepest assumptions about ourselves. How would we respond to such a revelation? What protocols should be in place for contact, for initial communication, for managing the influx of information? These are not questions for tomorrow, but for thoughtful, calm consideration today, developing frameworks for a future that might arrive unexpectedly. The field of planetary protection, on the other hand, deals with a more immediate and practical ethical responsibility, one that we actively manage in our space programs. As we send our robotic emissaries to other worlds, particularly Mars and the ocean moons like Europa and Enceladus, we have a profound responsibility to prevent two critical types of contamination. First, forward contamination, ensuring that we do not inadvertently carry Earth microbes to these pristine environments, potentially contaminating them, and making it impossible to determine if any life found there is truly indigenous. Our spacecraft are meticulously cleaned in clean rooms, gently baked at high temperatures, and carefully sterilized to minimize this risk. A quiet, diligent effort. Second, backward contamination, ensuring that any samples returned to Earth from potentially life-bearing worlds do not introduce harmful alien microbes to our planet, protecting our own biosphere. This requires incredibly stringent containment protocols, much like a quiet, invisible shield around any return samples, until they can be safely analyzed. These careful, methodical steps reflect a deep respect for the potential for alien life, and a profound sense of stewardship for our own biosphere, a quiet, ethical duty we undertake in our cosmic explorations. As we gently bring this extensive exploration to a close, let us reflect on the profound impact and cosmic significance of finding life, whether microbial or intelligent, and the enduring human drive for discovery. The universe, in its quiet, vast majesty, has always invited us to ponder our place within it. Finding life beyond Earth, even the simplest microbe thriving beneath an icy shell, would instantly transform our understanding of life itself. It would tell us that life is not a miraculous fluke, an isolated phenomenon, but perhaps a common, quiet expression of the universe's inherent chemistry and physics, a natural unfolding. It would connect us to a larger biological tapestry, gently weaving through the cosmos, uniting us in a shared biological heritage. And if, one day, we were to detect an intelligent signal, a deliberate message from across the stars, it would forever change our philosophical outlook. It would confirm that intelligence is not unique to humanity, inviting us into a grand cosmic conversation, however slow and deliberate that conversation might be. This would be a moment of profound cosmic humility and connection, a quiet realization that we are but one voice in a vast, intelligent choir, a testament to the universe's boundless potential. The hunt for alien life is a journey driven by the deepest human impulses, curiosity, wonder, and the yearning for understanding, a fundamental desire to connect. It is a patient, methodical quest, relying on the quiet dedication of scientists and the slow, steady advance of technology, pushing the boundaries of what is known. The universe continues to unfold its secrets with quiet grace, revealing its wonders one discovery at a time, and we, as a species, are slowly, gently learning to read its ancient script. In this grand cosmic quest, we find not only scientific revelations, but also a profound reflection on ourselves, our fragility, our resilience, and our boundless capacity for wonder. May your own journey through these thoughts be a peaceful one, leading to a quiet rest, filled with the gentle hum of cosmic possibilities and the silent promise of future discoveries. As our cosmic journey through the hunt for alien life, every method, every discovery, every possibility draws to a peaceful close, take a moment to let these wonders settle in your mind like stardust drifting through space. From the smallest particles to the grandest cosmic structures, everything we've explored tonight is part of the same magnificent universe that cradles our small blue planet. As you drift off to sleep, remember that you are made of star stuff, connected to every distant galaxy and cosmic phenomenon we've discussed. The universe is vast, beautiful, and filled with endless mysteries waiting to be discovered. But for now, rest well, knowing that tomorrow the cosmos will still be there, patiently waiting for curious minds like yours to explore its secrets. Sweet dreams, fellow space travelers.